In this video, we are studying projectile motion and we will derive some equations that will be useful in doing projectile motion problems. As a reminder, projectile motion is the motion that an object takes through the air when only under the influence of gravity. We have already written down some equations that describe the motion when given the following initial conditions. You start with a velocity v naught that makes an angle theta from the horizontal. Using these initial conditions, we can break the problem into components and write down the velocity and the position in the x and y directions. What we find is the x direction has a velocity that is constant. It does not depend upon time, and the x position increases linearly with time. The y position has a constant acceleration equations that we recognize from the constant acceleration. We have a linearly changing velocity, where in this case it is decreasing with the acceleration minus g, and we have a y position that, as a function of time, makes a parabola. Using these four equations of motion, we can find the position of the projectile at any time t after it is fired. However, sometimes the problems do not need this time information, and we can simplify our life somewhat by combining some of these equations to get rid of some variables. The first equation we will look at that does that is actually called the trajectory. This is an expression that gives the position y not as a function of time, but as a function of x. To do this, what we need to do is solve the horizontal position time equation for time and substitute that into the time in the vertical position time equation. So for the first step, we will solve the horizontal position time equation. And then we will substitute that in for time to the horizontal position time equation. A little simplification where we combine the sine and the cosine to a tangent gives us our final expression. Y as a function of x is equal to the initial y position plus initial velocity times the tangent of theta times the change in position minus gravity over twice the initial velocity squared times cosine squared theta times the change in the x position squared. What we can see is that with this equation we have the y position as a function of x that depends on x and negative x squared. This tells us that the trajectory through the air will be a downward facing parabola. This trajectory equation is important enough that we will copy it and use it as one of the general equations for projectile motion. The next equation that we will be interested in is not a general equation. It is a special case, but it is a very important and very useful special case. And that is, what is the range that we can fire a projectile when the initial height and the final height are the same? Again, the condition necessary in order to use this equation is that the initial height and the final height of the projectile have to be the same. When you get this, you get what we call the range equation. We can derive the range equation by combining the y position time and the x position time equations and getting rid of time. Now the special condition is that the initial and final velocity or initial and final heights must be the same. We will set those equal to 0 for simplicity. It says y final equals y initial, and we're going to get rid of both of them on each side. We are now going to solve this equation for time and substitute it into our position equation. Solving for time, gives us two solutions. We have 0 is equal to the initial velocity in the y component, which is vi sine theta, minus a half times the gravity times the time interval that it was in the air, whole thing times the time. So we have t equals 0 as one solution, and we have t is equal to 2 initial velocity in the y direction, vi sine theta, over gravity. The t equals 0 obviously refers to when we first fired the object, the projectile, and so it is not going to be relevant for our problem. We are interested in the second solution. Taking that second solution, substituting it back into the initial equation, we have x final is equal to x initial plus v initial cosine theta times time, and now we're going to substitute this in, 2 v initial sine theta over g. For the final thing, we're going to define the range as the final minus the initial position. So the range is equal to vi squared over g times 2 cosine theta sine theta. The last thing we're going to do to simplify this problem is we are going to use the trig identity that 2 cosine theta sine theta is equal to sine of 2 theta. This gives us the range equation in the final form that we see it in the book, which is the initial velocity squared over gravity times the sine of 2 theta. Erasing the details of the derivation, let's examine one of the properties of this range equation. What angle do you need to fire a projectile in order to get the maximum range? Looking at this, we can see that sine of 2 theta takes on several values. We know that sine of 0 is equal to 0, and we know that sine of 90 degrees is its maximum, which gives us 1. So we have that 2 theta should be equal to 90 degrees at maximum range. That says that theta should be 45 degrees for maximum range. These two equations, the trajectory equation and the range equation, are useful equations to use when solving some projectile motion problems.